All right, welcome back. Section 4.4 mean value theorem and the second fundamental theorem of calculus. Let's get started and let's figure out what we got to do here. We're going to do mean value theorem. We're going to do some second fundamental theorem of calculus. We're going to find some average value. We're going to do some awesome sauce on this problem, on this note page here. So here's the mean value theorem. Okay, remember we had a mean value theorem for derivatives where the instantaneous rate of change was equal to the average rate of change. And so that was for derivatives. Now we have a mean value theorem for integration. And what it's saying is that if it's continuous, if the function is continuous on a closed interval, then there exists a number c in the closed interval such that the integral, so this is the area underneath a curve, is equal to some point, some y value, times the height or the width of that rectangle. So basically it's saying that the rectangle, so this is f of c right here, okay, and if I find that actual area of the rectangle from this is a to b, okay, that's where b minus a is from, so this is b minus a is some value, okay, times the height of that rectangle, that area, this is going to be equal to the area underneath the full curve, which is all right here and then all included there. Okay, so basically what it's saying is this little piece that's not filled in is equal to this little piece that we're taking the area of, that f of c times b minus a. That is what the mean value theorem states. There's some value that the area with the f of c rectangle is equal to the full area underneath the curve, okay, from a to b. Let's keep going. So in other words, I think it's a song, right? Or like maybe Frank Sinatra or something. In other words, there exists a c between a to b such that the rectangle would have the same area found underneath the curve. Fantastic. The mean value theorem only tells you f of c exists. In order to rearrange the equation, you find the value of f of c. So this is what you're probably a little more familiar with, which is here. So this is the average value of a function, very, very, very important. Okay, but basically the mean value theorem for integrals. It's saying that f of c, so f of some value, is equal to the average rate, the average value of the function. Sorry, okay, that rate of change is derivatives. Average value is integrals. So 1 over b minus a times the integral from a to b of f of x dx. So in this case, basically the area in this box, okay, here is equal to that there. If I subtract some values, right, you're going to get that value of the full function. And so now let's get into an example of average value. So what I want to do is I want to find the average value of this function, 3x squared minus 2x, on the interval from 1 to 4. So I know the average value is that f of c piece. That's equal to 1 over 4 minus 1, right? This is a and this is b. Of the function from 1 to 4, 3x squared minus 2x, and all of that is being dx'd. Okay, so if I do this, so this is 1 over 3 from, actually I can probably just integrate that right now, right? So let's integrate it. This is going to be x to the third. Really it's x to the third over 3, but that 3's cancel, minus this is x to the 2 over 2, but that 2's are going to cancel, so minus x squared from 1 to 4, so that's pretty easy, equals 1/3 times 4 to the third is 64 minus 16 minus 1 plus 1. Okay? Because technically, let me actually show you what I'm doing here. So it's 64 minus 16 minus, now I'm plugging in the 1, so 1, and then this is also minus 1. Okay, so 1 minus 1 is 0. Alright, but that's just going to cancel, right? It becomes 0. Fantastic. So this is going to be 48, then times 1/3, which is going to be 16. So f of c is equal to 16. Okay, great average value. Fantastic. Let's go to some second fundamental theorem of calculus. The second fundamental theorem of calculus basically says that if f is continuous on an open interval containing a, then for every x in the interval, if I took the derivative of the integral, then I just get f of x. So just this f of x piece right there, it kind of goes down. So if the upper limit is a function, So in this case here, so in this case it was x, so just some value, okay, some value. If I took the derivative of the function where the upper limit was a function g of x, then when I plug g of x into f, I have to multiply by that g prime. So that's the chain rule piece that some of you guys forget. All right. The upper limit must be the variable. So if the lower limit is x and the upper limit, we need to switch the upper limit there. So if a is the number and x is the bottom value, then we just flip that around, and then when we do that, we get the negative of that integral, and we can do that very same process. The second fundamental theorem of calculus shows that if a function is continuous, then it will have an antiderivative, and the antiderivative may not be an elementary function, so that might not be an easy thing to do. An elementary function is written with one variable and is made up of a finite number of arithmetic operations. So for instance, all of this. For example, the integral of e to the x squared dx does not have an elementary antiderivative. So the antiderivative is not going to be an easy one to figure out. We will figure this out later on this year. It's called integration by parts. We could do u substitution, but that's going to be really crazy. And it might not work out great, but we'll do that integration by parts. But it does have an antiderivative nonetheless, so it's going to be a harder one to find. All right, so here's some examples. Let's do some of those. Let's see how we can get, how we can do here. So this is saying that if I took the derivative of an integral, okay, derivative of an integral, all I do is plug this into here, so I get the square root of x squared minus 1, and then multiply by 1, which is the chain rule of that. So the derivative of x is just 1, so this is going to be your answer there, right? So it's really just square root of x squared minus 1. This one, I'm going to take the x to the third, okay, find the slope here. So what's the slope? Well, I'm going to take the derivative, right? So if I took the derivative of this, so basically I'm saying I'm taking d of all of this over dt, because that's what the function I have. And I'm going to plug this in, so it's the cosine of x to the third squared, so that's x to the sixth, multiply by the derivative of x to the third, so 3x squared. So 3x squared times the cosine of x to the sixth. This is your derivative. Okay, remember derivative is slope, so that's all I want to find. I don't want to find any values. That's not what I want. Now, I want to find the derivative of this, okay? But because the sign is on the bottom, it's going to be negative 2 to sine x, and then cosine t plus 2, all right? With all of that dt'd. So what do I got to do? Well, that negative is going to pop out. The sign is going to go into the t, so it's going to be negative cosine of sine x plus 2 times the derivative of sine, which is cosine x, right? So this is really negative cosine x times cosine of sine x plus 2, and close brackets there. Or we could multiply out and you would get, do I want to multiply out? No, I don't really want to multiply out. I'm good there. I get cosine. Yeah, I'm good. Let's do that. Let's leave it there. That's fine. Leave it just like that. All right, don't want to multiply out. That would be crazy. Okay, last one here. So the graph of the function f consists of the quarter circle. So this quarter circle with some line segments like piecewise functions, right? So here's what the graph is defined as. So I want to find g of 0, g of negative 1, 2, and 5. So g of 0 is going to be the integral from 0 to 0, because I got to plug this 0 into that x right there, of f of t dt. But hopefully you remember that if I have the two of the same bounds on the upper and lower bounds, that's always going to be 0. You don't have to show any work. That's always going to happen, right? That's one thing you need to know. G of negative 1 is equal to 0 to negative 1 of f of t dt, which is equal to negative, because that's on top, so it's negative 1 to 0 of f of t dt. And what that means is from negative 1 to 0, so I'm finding the area of this rectangle, which is 1, right? Base times height divided by 2. So that's 1, but then I have a negative, so it's negative 1 out front. All right. What else? We got g of 2. Let's go g of 2. That's equal to 0 to 2 of f of t, f of t dt. And that's going to be equal to, from here to here, So our radius of this circle looks like to be 2. So it's pi r squared. Okay, divide by 4. So it's pi r squared. Divide by 4. The radius is 2, so 2 squared is 4. 4 divided by 4 is 1. So that's just pi. Fantastic. So that's what our g of 2 is equal to. It's just pi. And then I have g of 5, and that's equal to the integral from 0 to 5 of f of t dt. And so if I know this is pi, and that's 2, 3, 4, 5, so right here I'm going to find all of this area down there. And all that area is going to be negative, right? Which, if I look at it, this is right here, this rectangle is minus 1. And then this area here is basically a rectangle, or it's well, it's a couple ways. I can split into a rectangle, so that's 2 or minus 2, and then this triangle is also minus 1, so that's minus 4. So all of this up here is minus 4, and so we know that it's pi minus 4, which is just pi minus 4. I don't have to do anything else from that. So that's what g of 5 is. Okay. Find the x-coordinate of each point of inflection on the graph of g on -1 to 5. Let me erase all of this there. And then justify your answer. Okay, let's do that. Let's go back to this. Okay, so what do I need to do? So point of inflection is I need to find the second derivative. Well, if this is the original function here, then that means that g prime of x is going to be equal to f of x. Okay, remember I got to plug that x in and then multiply by 1, so that's what I get. So that means g double prime of x is equal to f prime of x. So the first derivative there. All right, and then points of inflection will occur when the slope changes signs. So I'm going to say POI, points of inflection, changes when the slope changes signs. Okay, so when the slope changes signs. So when does that happen? Well, the slope changes signs when x is equal to 0, because my slope is positive and then now it goes negative. So it changes slopes there. And when x is equal to, well, that's all negative, 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 negative. That's still negative, 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 negative. Now it's positive, so that's at 4. Okay, so the slope changes. Oh, man, I can't count. Oof. I was wondering why it wasn't working. Okay, this is 3, x equals 3, not 4. What was I doing? I paused for a minute and checking my work, and man, I'm telling you, I'm going crazy. Okay, so there we go. Points of inflection changes when the slope changes signs. So in order to figure that out, we just look at the graph. Where does the graph change slope? At 0 and at 3, and then that's all that I needed. All right, that is the end of this video. I will see you in the next one. Deuces.